So you know I'm kind of obsessed with normal modes right now. I made some previous videos on normal mode for coupled oscillations. I'll link those down below. In the last video, what I did was, okay, so what's a coupled oscillator? I should start from the beginning. So imagine I have two masses and connected by these springs. So the motion of this one affects the motion of that one because there's a spring connecting them. We can write down the equation of motion for mass 1, which I'm calling the position x1, with this x1 double dot. That's mass times acceleration, and that's the net force on mass 1. And this is the net force on mass 2. And you'll notice that mass 1 has an x2 in there, mass 2 has an x1 in there, so that's why they're coupled. Now, one of the things we want to do is to find a normal mode. A normal mode, I'll show you in just a second, is when these two masses have the same angular frequency. They move with the same angular frequency. If these two springs are the same and these two masses are the same, one normal mode is where they move like this. Another mode is where they do this. And I'll show you that in just a second. So in the previous video, I found the normal mode frequencies and, more importantly, the initial conditions by assuming x is a vector. The position is a combination of these as a two-dimensional vector, where a1 and a2 are constants in that equation. And then we assume e to the negative I omega t, and then we'll take the real part of that. And if you do that, we can take the derivative and get that, and turn these two equations into the following matrix equation. And this says, here's some matrix, which is based on these x's and m's, and there's my vector. I want to operate this on a vector and get the same vector back with a scalar, and that's the eigenvalue problem, and I did that. But I want to do it another way, right? Because dealing with determinants stinks. And I don't like that. So let's jump, and I want to show you the two normal modes, and then I'm going to explain how I'm going to find the normal modes without this eigenvalue problem. And just for fun, right? It's just for fun. And profit, maybe. I don't know. Okay, so let's go over here. This is the program I made before. This just shows the masses on a spring, and this is one of the normal modes. Let me go ahead and play this. This is the one where they're moving in and out like that. And the amplitude is a little large, but that's fine. And then you can see down here a plot of their position. They have the same frequency. They don't have to have the same amplitude. These two masses aren't the same mass, I guess. That's strange. Let's just check, because I was playing around with this. So here I have K1, K2. Yeah, they're different. So let's put these both the same mass. K1 is the K2. Let's put this at 10. Okay, there. Oh, and then I did this. Okay, let's just change this. Let's say x1 equals 0.03, x2 equals 0. So this is no, this is not a normal mode. That's not a normal mode. Notice they do not have the same frequency. Okay. Now, if they both have the same starting position, they do have the same normal mode. So if I put this at 0.03, this is a normal mode. Like that. Okay. They do have the same frequency. That's important. And then the other normal mode is if they're opposite. But this is easy. You can do this without a matrix if they're equal masses and equal spring constants, stuff like that. But what if they're not? That's the question. Okay. So one of the important things is that, let me go back to the paper so I can show this. These A1 and A2 are if, let me put the if here. If x1 dot of 0 is 0, x2 dot of 0 is 0, then these coefficients x1 of 0 is A1, x2 of 0 is A2. So those coefficients are the initial positions, and which is really nice. So now what I could do is just change these initial positions until I get a normal mode, and that's what I'm going to do. So imagine this. Imagine that I have A1 versus A2 in 2 dimensions, and I pick some initial vector, because it is a vector, at some angle theta. And then what I'm going to do is to change that angle theta. This will give me A1, A2. So I can say A1 is, let's call it just A cosine theta. A2 is A sine theta, and then I'll just change theta, and I'll just look and see what happens. So let's go ahead and do that. Let's do our simple coupled oscillator program, which just uses Newton's second law, and I'm just going to vary the initial conditions. So going back over here. So I have another program already set up right here. Let's see if I run this. Yeah, this is just coupled oscillators. That's all it is. Now I did have to modify it. I want to have x1, x2, x3, m1, m2, not just x, b, and m. So if you look over here, I have two different masses, m1, m2, and three different spring constants. I set them all the same so that what it was before, so that's all cool and fine and dandy, everything like that. So but what I want to do now is to change my initial conditions x1 and x2 based on this theta. So let's just go down here and say A equals 0.03, and it could be anything. That's just the amplitude. As long as they have the same amplitude, it works. And then I will say, let's call this A1, because I'm using A down below. See, down here, I just calculate the acceleration of each object using Newton's second law. Use that to update the velocity, use that to update the velocity, use that to update the position. So I'm going to call these capital A1 and capital A2, not to confuse with the accelerations. So A1 is going to be A times cosine of theta, which I haven't said. Theta equals 0. Let's just do that. And then A2 is A times sine of theta. And that just sets the initial conditions. That's all that does. So in this case, if theta is 0, then I should have the same thing, because this is going to be 0.3, that's going to be 0, and that's going to just be your normal. But what I want to do is to make this graph, change theta, remake the graph. Okay, so that means I want to animate the graph. This is going to be great. We're going to make an animated graph. So the first thing I want to do is all of this stuff from here down here, I want to put this all in a loop. So let's put theta as 0 up here. Theta equals 0. D theta equals 0.01. Now, while theta is less than 2 times pi, I'm going to go all the way around the circle. I'm going to do all possible combinations of A1 and A2. I don't have to, but I'm going to. And let's make this do it at 100 times per second. But all this stuff I want to redo, right? So I'm going to indent all this stuff. Tab. It's going to be part of the loop. And that one I want to rate. This one I do not want. I can't have two rates. It makes it messed up. So I'm going to go down here. I'm going to calculate everything I want. And then I'm going to update theta. So let's put the theta equals theta plus d theta right down there. If I forget that, it'll run infinite. So what's happening down here, I need to recalculate A1 and A2 every time I go through the loop, and then I rerun everything. I got to reset t equals 0. I got to reset the initial conditions. Oh, should be x1 equals A1, A2, x2 equals A2. I didn't even do that before. It didn't matter. It would have worked. Okay, now I do have to do something about the graph, because to make an animated graph, what you want to do is to take all your data and add it into a list and then graph the list. So it's a little bit different, but I can do it, and it looks awesome. So let's go down here. I'm going to make, let's call this F1 data. Let's call it data 1. Data 1 is an empty list. Data 2 is an empty list. And then down here, I'm not going to plot, right? I'm going to get rid of these. Instead, what I'm going to do is just add data to a list. So I'm going to say data 1 equals data 1 plus t, and I was plotting x1. And then down here, data 2 equals data 2 plus t x2. Okay, so that's how you make you add pairs of data to a list. So it's a list in a list. And up here, I'm setting, at the beginning of the loop, I got to clear the data, right? So that's what I'm doing right here. I'm clearing the data, and then I'm adding to the data. Then when I get done with this loop, I have all my data. I want to plot it. So I can plot it like this. f1.data equals data 1. And you can call it whatever you want. You need that dot data, but data 1 can be anything. f2.data equals data 2. and then it'll plot it and it'll update data and it'll go back again. I think this will work, but I always make mistakes. Let's just see what happens. If it runs, it's going to be awesome. There you go. Okay, so these are my x1 and x2 plots as I'm changing the initial conditions. And you can see there are certain cases right there where they have the same frequency, and they're going to have another one right here, same frequency and same amplitude because everything was the same. And so we're going to go through and find those values. I want to find out what values of data gives me those matching things. I just love that graph. Let's plot it again. Just, come on. Sometimes you win, and that's a win right there. That's a pretty nice graph. That's what's so great about animated graphs, which are really easy to do in Web Python, which is what I'm using. It's just art. It's not just physics, it's art. Okay, so now what I want to do is to, how do I know when they have the same frequency? Well, one thing I could do is to take the difference of x1 and x2, right? And if they're exactly in phase, x1 minus x2 would be 0. But if they're exactly out of phase, it wouldn't be 0. So what I want to instead do is to take the difference of the absolute value. And then it doesn't matter if they're in phase or out of phase, right? And so I'm going to do that for every single point in here. And then what I'll do is take the difference, so I have a list of differences, and then I can just average it. That'll be the best way to take into account the whole data set. So I'm going to take the absolute value of each point, subtract them, add it to a list, and then I'll average it. Is that a lot? That's a lot to do. That's fine. We can do it. Okay, so let's do this. And then I want to plot that average, that absolute value of the difference. The absolute value, and then the difference as a function of data. So I want to see when that difference is the smallest, because that's when they're in a normal mode. So I want another graph. Let's make another graph. In Python, Web Python, if I just make another graph, G2 equals graph, title equals, let's give it a title, difference. And then I'm going to say X title is theta, Y title is, let's call it ABS difference. That's good enough. And then let's give it a width, same width 500, height 250. The other one I put max and min values just to make it, when you do an animated graph, you don't want it to zoom in and out, so I did that. And then I need something to plot there. Let's just call it F3, and it's a G curve, color equals color.blue. Okay, so now what we're going to do, I want to, every time I make a plot down here, every time I do one of these plots, I want to add the difference to a list too. So I'm going to make a new list. Let's call this diff data. And it's just an empty list. Again, clear the list because I want to average that. And then down here, when I'm plotting, I'm going to say diff data equals diff data. This is, I like appending lists with the plus square brackets. You can use the diff data dot append. I just like this better. You do it the way that makes you happy though. So I want to take the absolute value of x1, subtract the absolute value of x2, and add it to that. So let's say ABS is the absolute value built into Web Python, x1 minus ABS x2. And so now I have that data. Now down here I plotted the animated data. I want to plot this, the average of this. So let's call this diff, a diff. It's going to be average. Average is built in. Average, which I didn't know until just recently, diff data. So that's going to return. That's going to go through and average all those values in that list and return the average value. Now I can plot that. So let's say f3.plot theta a diff. I think that should work. Yeah, did I not say this? In Web Python, if I have two graphs, you can assign which curve goes to which graph, but if you put them in order, it figures it out and it's fine. I should save this. I will give you the code. Okay, let's run this. And there's an error. Can't find the variable height. Height equals. Okay, there's that. That's working. Okay, so here's my difference graph, and that's not what I completely expected. But you notice it is crossing these points right here. It should do it. There should be 2 normal modes, but since you go all the way around the circle, you should actually get 4. So 1 right there, 2 right there, 3, 4. But let's just do this. I don't like that. Let's do this. Let's plot the absolute value of the average. So diff data average. Where's the average? Where did I find the average? Oh, here it is. Let's just take the absolute value of that. That way we can see when it hits 0. It's easier to see when it hits 0. So there's that. Kind of hard to see when this goes to 0, those do match up. Let's see if I can make this a little smaller. Yeah, let's run that again. So watch the 2 together. And when this goes down, I'm pointing at the screen, doesn't matter. When this goes to 0, these are lined up, either in phase or out of phase. So let's run that. So it seems like it's working. Bink 0. See? Okay, that's pretty cool. But now I want to know I could go on the graph and say, okay, there's my theta value. I can just get it off the graph. But I want to do it automatically. So here you see the values of the absolute difference are pretty small. This is 0.3 times 10 to the negative third. So I want it smaller than that. I want to say if the difference is smaller than that, then print out theta and calculate A1 and A2 just so I can see what they are. I could print out I'm not sure about finding the frequency, but let's not worry about that. Okay, so down here, I'm going to say I calculate my average difference to make this big again. And then I'm going to say if A diff is less than, let's say, 1 times 10 to the negative fourth. I'm taking a guess here, right? Because it may not get that small because I'm doing things by chunks. If it's not, I'll do it again. If that's the case, then print theta equals theta. And let's print A1 and A2. So print A1 equals A times cosine theta. Print A2 equals A times sine of theta. Let's see what happens. It may not print. Like I said, it may not print. Because it may never get that small. And it may print more than 1. Okay, so it did. So it's printing it twice, 3 times. It's printing it several times. Let's make that a little bit smaller. I want to make it smaller. Let's say, what if I do 1 times 10 to the negative fifth? Let's see if that's too small. Because it's getting multiple values that are lower than that threshold. Now it's getting no values lower than that threshold. So that's too small. Let's make it twice as big. So let's just do 2. Let's just see. Yeah, I am playing around with this, but nope. Oh, it did get it. Okay. So it got 2. It got 2 values here. That's fine. I'm pretty happy. So let's look at these values. So this first one is at, it doesn't really matter what the theta value is, 0.78. That's pi, wasn't that pi over 4? But you'll notice here that A1 and A2 are the same. So that's the same motion. They start with the same initial position. That's what we said before. The next one, that's again the same value. That's 0.79, 0.78. It's just they're both below the threshold. This next one is at theta is, let's see, pi. So that's, well, I don't know what the value of that is. But this is the other normal mode, right? One's negative and one's positive. So that's this motion. Now the other ones are redundant. Here's the same. That's the same thing. Here's this. They're both start off negative, which is this motion again, where I had that one. And then here is the other motion where one's negative, the other one's negative, the other one's positive. So again, that. So we got all the normal modes from this. Now, the true test, right? The true test. What if they're not all the same masses? What if it's not a simple situation? Let's see if this works. Okay, so let's change I kind of want to make like K3 small or 0. Let's make K. What if I make K3 0? So that means the spring on the end, I just take it away. Let's see if this works. I don't know if it's going to work. So K3 is 0. I'll say times 0. And let's run it again and see what happens. Let's see if they even get... There was a normal mode, and there it is right there. There's another normal mode. Let's make this small. We got to watch these two together because it's just awesome. Let me rerun it. Okay, it looks like it's working. Let's see what kind of values we get. 2. We should get 4. 3. 4. There we go. I was going to get, okay, good. And so the values we get, oh, it only gave me 1. I need to make my my threshold larger. But that's fine. Let's put these in. Let's put these in. So let's go back over to my testing normal modes. This code right here. And let's put, I have the same, no, I don't. Do I? Let's just copy. I want to test it. So, okay, let's just do this. I'm going to copy this for A1. So that's going to be X1. And then K1 was 0. I don't know if it's the same value of the masses and if that matters or not. And then this is going to be the other one, X2. And then let's see if I have a 0.19, what's my mass? 0.15. Okay, so let's change this to 0.15. But everything else is the same. So that way we can just see what happens. No, that didn't work. Oh, did I change that? K1, K2 is 5. K1, K2 should be the same. Let's make this a little bit bigger to catch those things. A1, A2. Let's see if we get the other one. Oh, see, that one has a positive. That didn't get the second one. Okay, let's... Oh, it got this one. That's the one we got before. But that's the same thing. Let's make that a little bit bigger. 1 times 10 to the negative 4th. If that's not big enough, then we'll just carry on. Okay, so that one, it got theta. It didn't get that one. You see, that's 10 to the negative 2, that's why. Okay, one more time. 10 to the negative 3. I don't want to have that too large. I'll get too many values, and then that makes me just like, oh. Okay. Theta. Okay, we're getting too many now, but that's fine. So it's printing a whole bunch. Way too many. 0.1, 0.2. Doesn't seem like it's working. X1 is 0.1. Let's put this at 0.1. Let's just try 0.1. Or 0.2. 0.1. Okay. That seems to be working. And that spring, although it's moving, it's not actually there. Okay. Okay, I'm pretty happy. There is another way you could do this manually. And you could use the eigenvalue problem, the same thing, the matrix, and do and pick a vector and just multiply it into the matrix. I might make that. I did that before for a moment of inertia tensor, but I'm not sure. This works with 2 degrees of freedom. If you have 3 degrees of freedom, you can still write the initial vector in 3 dimensions, but you have to move it in 2 directions in order to find those minimums, which is kind of a challenge, and I want to do it, but I'm not going to do it right now. The next thing I'm going to do actually is to do normal modes for 3 masses, 4 springs, because I think that'll be fun. Okay, the end. Code down below, links down below. Have fun.